Good evening, sir.
Yes, good evening. Yeah. So just I'm continuing from the yesterday's session, right?
Yes, sir.
Sir, today also can we end by 6, sir?
Yes. By 6 only I will be finishing it off because we already
Mostly we
completed
finished
almost.
it, sir.
Yeah, only one topic. This one remains.
Yes.
Yes,
Okay,
sir.
the next continuation of the yesterday's session. All right. So we discussed about electric motor, right?
Yes, sir.
Okay. Why that electric motor gets rotated?
Sir, because of electric and magnetic forces.
Yes, because of electric field, magnetic field is produced. That magnetic field interacts with the permanent magnet.
Yes, sir.
Thereby exerting some force on the conductor. That conductor rotates if it is in the shape of rectangle or
Yes,
square.
sir.
Yeah, that's the thing. If it is like a rectangle or a square, there is torque acting, that is called couple. This is also known as couple,
Yes.
which is responsible for rotation of the object. So whenever you want to make any object rotated, then what is the requirement is a couple of forces, not a single force. So when you can remember this one, this is very useful in mechanics also.
Yes.
So if any object is in rotation, definitely there must be two forces acting. They must be equal and opposite, but their point of action is different.
Yes.
Yes. So today we are discussing more about the magnetic field produced by electric fields.
Yes, sir.
The actual term is known as electromagnetic induction. This is called electromagnetic induction. Is there any, how it happens? It depends on what now you can see. Is it visible?
Yes, sir.
Okay, just here you have a coil. This coil is known as, you know very well. What is the name of this coil?
Solenoid.
Solenoid. So to this one, now I connected a bulb, right?
Yes, sir.
Okay, I am having one bar magnet, right?
Yes, sir.
Okay, is there any magnetic field because of this magnet? Yes, there is a
Yes,
magnetic
sir.
field. You can see the magnetic lines of force. Okay, okay, shall I move it?
Yes, sir. It's detaching.
Not detaching.
The bulb is turning off.
It is not detaching, it is just the magnetic lines are interacting with the magnetic lines or magnetic field produced by that coil, right?
Yes, sir.
Okay, that is a symbolic indication. It doesn't mean that they are getting attached.
Yes, sir.
Right?
Yes.
So that field variation, now you can see. When it is coming closer, the interaction is more, so that voltage is more, right?
Yes.
Am I applying any current now?
No, sir.
No. Isn't it?
Yes.
But in the case of motor, electric motor, what we were doing? We were supplying some current through that coil, right?
Yes, sir.
Yeah, through the coil, we were passing some current. That conductor carrying current is placed in magnetic field, but we are not supplying any current now, right?
Yes, sir.
But simply what I am doing, previous activity you might have observed in the previous activities. You might have observed that magnet is completely static in nature, right?
Yes, sir.
It was placed like this. But if some current is passed through the coil, it becomes a magnet. That's what we understood.
Yes, sir.
Okay, now I am not at all sending or passing any current through this coil, but what I am doing instead of it, what I am doing? I am moving the magnet.
Yes,
You
sir.
can see. Because of this movement of the magnet towards the coil, what is the behavior of this coil? How this coil is behaving? This coil is also behaving like a magnet, right?
Yes, sir.
Okay, this magnet, but the magnetic field, is the magnetic field constant? That's the point. Is it constant? The magnetic field that is experienced by this coil, is it constant or changing?
Changing, sir, maybe.
Just observe. That's what these magnetic lines. If the magnet is away from the coil, do you see any magnetic field around the coil? Do you see any magnetic field? Is it observable when the magnet is away from it?
No, sir.
No. Means magnetic field is almost zero then, right?
Yes, sir.
When the magnet is very close to the coil, very close to the magnet, very close to the coil, the magnetic field is maximum, right?
Yes, sir.
So the magnetic field is varying between 0 and maximum, or I can say minimum and maximum, right?
Yes, sir.
So this variation of magnetic field is producing what? Is producing what? Because
Electricity.
yes, electricity. Exactly correct. So if I want to produce electricity, what should I do?
You have to put the magnet closer.
Put the magnet
Closer.
close to the. Okay, if I just keep that magnet very close to that coil and then leave it, what happens? If the
Then
magnet
maybe
is
we'll get electricity.
okay, is there any electricity now?
No, sir.
Then, so if I want to get electric current or electricity, what should I do? What should I do? This magnet should keep on moving, right? Exact point. This is the principle. Who is the first person observed this one?
Ampere.
No. Famous personality. Michael? You know the name?
No, sir.
Michael? Can you guess at least?
Faraday.
Name is Faraday.
Faraday.
Michael Faraday. He is the first.
Sir, you are not audible, sir. Sir.
Changes.
Go ahead.
Okay, if I rotate, can I see the same thing? Hello?
Sir, you're not audible.
So yeah, just a disturbance in internet. Am I audible now?
Yes, sir. Clear.
Okay, yeah, now it's coming up. Okay, now what I did is, this is called linear motion, right?
Yes, sir.
Traveling along a straight line, right?
Yes, sir.
But instead of this, Okay. If I rotate, will there be any current in that coil? What is your guess? Hello?
Yes, sir.
In the beginning, I showed that when magnet is moving along straight line, or I can say to and fro motion, right?
Yes,
Towards
sir.
the coil and away from the coil, to and fro motion. This is the linear motion. Then we observed some current in the coil and bulb has blown, right?
Yes, sir.
If I rotate the magnet, will there be any current?
Sir, maybe there won't be, sir.
Shall we try?
Yes, sir.
Is there current or not?
It's there, sir. It's there.
It's there. Whatever it may be, the motion of the magnet, whether it is a linear motion or rotation. Which one is easier for us?
Rotation. Rotation, sir, because current
yes.
is long.
Rotation will be the easier one because the distance we can maintain a constant and then we can make it rotate at the same point with respect to the same axis, right? So this principle is used. Where is this principle is used? So this is how actually electricity is generated,
Yes.
right? Okay,
Yes.
suppose you ever visited the hydroelectric project?
No,
Or
sir.
no. Okay, where there is a turbine, right?
Yes, sir.
Do you see any turbine? What exactly the turbine contains? Turbine is nothing but a magnet, right?
Yes.
That gets rotated because of waterfall. Once this coil, this turbine is very close to that another coil, right? In that second coil, current will be generated. The same principle. This is the same, right? So if
Yes,
you
sir.
want to, yeah, I will show you just where exactly that one is. Yeah, there is another beautiful this one. I will show you just. Yes. Is it visible?
Yes, sir.
Okay, this is the magnet, right? Okay, this is the coil. Is it visible?
Yes, sir.
Okay, now what I do is I rotate the magnet. Now you right?
Yes, sir.
So this is how electricity is generated. Faster the waterfall, higher the electric current, right?
Yes, sir.
So there is another one. Okay, I just keep it rotating like. Right?
Yes, sir.
Okay. Now, how the magnetic field is varying and then everything you can measure. At each and every point you can measure the magnetic fields, right?
Yes,
Wherever
sir.
you want, you can see the magnetic field, how the magnetic field is varying. Is it constant?
No, sir.
Wherever you verify, at each and every point, that magnetic field is always changing, right?
Yes, sir.
This is the main point. If magnetic field is constantly changing near to the wire or like a solenoid, then in that solenoid current is produced, right?
Yes, sir.
This is a very simple principle. But the point is magnetic field around that coil should always change. Okay, for this one you can rotate the magnet, or you can move or to and fro motion of anyone. So the simplest one is rotation instead of to and fro motion. That is difficult to maintain, right?
Yes.
So rotation is easy. That is the reason why in turbines magnet gets rotated, and when it is kept close to another coil, right?
Yes.
Then electricity is produced. Okay, how many loops are there in this coil?
2 loops.
This one, 2 loops. If I increase the number of loops, will there be any increase in the current?
May not be.
Okay, just look at the bulb, right? I
It got
increase.
slow, sir.
Just look at the lines, length of these yellow lines, right?
It's getting constant, sir.
No. Okay, I reduce the now.
Now it's fluctuating, sir.
No, you look at the length of yellow. Is it reduced or increased now?
Reduced.
Reduced means number of loops now. How many are there? Only one.
1.
Okay, if I increase it, more glow.
More length is increasing.
More glow, isn't it?
Yes, sir.
Or if you want, you can see this meter. Then that will be clear for you, right?
Yes, sir.
Okay, now the deflection is more or not now? Just a bit increase. Okay, still? Now the deflection is very less, right?
Yes, sir.
So what does it indicate? The number of loops or number of turns in the coil is also very important.
Yes,
If I
sir.
have 100 number of loops in that coil, current will be still larger, right? Okay, what is there any effect of this area? Means radius or diameter of the coil. Will there be any effect? Okay, let me check. I am reducing that area. What happened?
It's slow, sir.
The maximum deflection, you look at the maximum deflection. I am increasing the area now, right?
Yes, sir. Now there is more deflection.
Deflection is more or not now?
Yes, sir. More.
So bigger the coil, more the current, right?
Yes, sir.
Okay, another point is also there, strength, right?
Yes, sir.
Magnetic field, this magnet's strength of the magnet. If I increase the strength of the magnet, definitely there will be an increase in the current, right?
Yes, sir.
So 3 factors. One factor is strength of the magnet. So if I use bigger and bigger magnet, then I will get more current. The second point, if I use more number of loops in the coil, I will get more current. If I use bigger area of the coil, definitely I am going to get more current. So, okay, now I will show you. If I, this deflection, maximum deflection, you can see very clearly. Now I am reducing, right?
Yes,
So deflection is more, right?
yes, sir.
Now the deflection is less. So the number of loops plays a very important role. Similarly, you can see the strength of the magnet. Strength of the magnet also plays important role. Another one is area. Area of the coil. Also, increase of the area of the coil increases the current, right?
Yes, sir.
Now we have 3 relations. If I combine all of them, I will get a formula, isn't it?
Yes,
They are
sir.
proportional. One is proportional or all are proportional?
All are proportional.
All are proportional. Current is proportional to B, proportional to number of loops, that is N, and area, A.
Yes, sir.
So I is proportional to A, I is proportional to N, and I is proportional to B or H, I can say, right? So is it clear now? This is the principle, right? Whenever magnet is rotated or moving around a coil, current is produced. Right?
Yes, sir.
Yes. Now more details. Whatever the thing that I showed right now, you have another beautiful demonstration. You can see there is a graph. You can see whether there is when exactly the voltage is more and everything, right?
Yes, sir.
What I am doing now? Just watch out, right?
Yes, sir.
I am making this magnet move through the coil, right?
Yes, sir.
Through the coil. Now this needle is deflecting, means there is, you can see here also, E means voltage, right?
Yes,
Look at
sir.
this. Now it is 0, right? Now slowly I move the magnet and you can see so whenever that magnet moves, there is a current. Whenever the magnet stops, there is no current, right? Or voltage, right? Okay, now I will show you the play. Slow view, I will, right? Just watch out. You look at this E value. Now you can see the graph. Okay.
Yes,
The
sir.
voltage that is produced is not always constant, isn't it? You can
Yes,
see,
sir.
right? This blue line.
Yes, sir.
Increasing and increasing maximum. Once again gets decreased and 0. And once again increased. So negative and positive, both are observed, right?
Yes, sir.
Now, once again, you look at the graph, you can understand very easily how that produced voltage varies. It is not a constant one, right?
Yes, sir.
So you can stop whenever you see that maximum, right?
Yes, sir.
Right?
Yes, sir.
Yeah, now you can see. So at what point that voltage is maximum? Is inside of this coil, how that magnet looks, right? The
Yes, sir.
changes, whatever the thing that we observed, right? Number of loops or spirals, length of this coil, right?
Yes, sir.
Means area, right? Is there any effect of this one or not? Now you can see. So if I increase the length, what happened? Voltage reduced, isn't it?
Yes, sir.
If it is a long one, but if it is a shorter one, it's a very shorter one. Now you look at. Yeah. What is the voltage now? Huge or not?
Yes, sir. It's blue.
It is huge, right?
Yes, sir.
Yes, that's the point. So you can increase the number of loops and verify. Now I go with 100, right?
Yes, sir.
Yeah, now you can see how close the loops are. Now you can see still bigger or low voltage. So huge, right? Large voltage is produced. So how much voltage I want to produce? The magnet is the same or not? Hello?
Same, sir.
The magnet is the same, but I am getting higher voltages. When? If I increase the number of loops, or if I have the very smaller coil with higher number of loops, right? This is called
Yeah.
density of the coil, isn't it?
Yes, sir.
Okay, any more? If I increase the speed, this magnet speed, right? Now I
Yes,
show
sir.
you. Now I remove that slow motion. First of all, I check with this one. This is the real time like, right?
Yes, sir.
Okay, now I reset. I increase the speed now, speed of the magnet. Still larger value of voltage or anything different. Okay, I will show you with very less speed, right? You
Yes,
watch out the
sir.
graph. Look into the graph, right?
Yes, sir.
You can easily understand. What happened?
It's getting smaller.
No, it is that vertical line is so big, right?
Yes, sir.
You will look at this one, right? Now I am slightly increasing the velocity, reset. Look at the graph, right?
Yes, sir.
Okay, now still I increase. Now you look at the graph. Now you see this gap, right?
Yes, sir.
Means quickly it is increasing and once again going to minus, isn't it? Now this gap had reduced or not?
Reduce, sir.
Reduced means quickly. This is called frequency, isn't it? Quickly it is changing positive to negative, right?
Yes, sir.
So if I increase this velocity of that magnet, quickly that current changes from positive to negative. That is called frequency. So if I want to alter the frequency of the produced current, what should I do? I will be increasing the velocity or movement of the magnet. So if I increase that acceleration, so you can see the effect of this, right? These are the magnetic lines. This is the graph. And these are the settings, right? So you play through this one more and then the questions are given and collect the information and then you can understand,
Yes,
right?
sir. Sir, your screen share has stopped.
Screen share. Stopped. Yeah. Is it?
Yes, sir. Now it is.
Yeah. So the information that you can collect is, first of all, select any one value for numbers, right?
Yes.
And you observe the voltage, maximum voltage and minimum voltage, right?
Yes.
And then you increase the length of this, find out the maximum voltage and minimum voltage. Similarly, go with the velocity, maximum voltage and minimum voltage. So like you collect the data and put all the data put into one table and then plot the graphs by yourself and then you can understand when this going to produce higher voltages, right?
Yes.
That's what we need. If I want to produce more current, then what are the points I need to consider? One is the number of loops, right? Very important. And density of it. Density means in smaller area, I have to pack more number of loops, right?
Yes, sir.
Okay, so I am moving to the next point. The same continuation of the same concept, right? We are using the same concept or same principle here, and then you just watch. Okay, it's I will quickly go to this one, right? Are you watching it
Yes, sir.
now? This is the charged particle, right?
Yes, sir.
This is the magnetic field I am applying. Inward means like this, right? So is there
Yes.
any force on the charged particle? Just you look for, is there any movement of it, right?
Yes, sir.
Is there any change in the direction of that?
No, sir.
I just, now I changed, right?
Now you changed it. Yes, sir.
Now you, is there any force or not now? The charged particle started moving around a circular path, right?
Yes, sir.
Okay, suppose if I take the positive. In this case, no force, right?
Yes, sir.
So here, if I change the direction of the magnetic field, now there is a force. This force is making the charged particle take the circular path, right? So
Yes,
what
sir.
is the direction of the force and everything? That's the only demonstration. Now this is, okay, instead of this one, straight away I go to this, right?
Yes, sir.
So this principle I already demonstrated, but you can see the graph and everything. So the settings are there. What are the different things you have? You can observe the effect of magnetic field, right? You can see the frequency. You can see the effect of surface area, right? Surface area of the coil, right? This is
Yes.
very similar to your, which one? Electric
That
motor.
wire one, sir.
Electric motor, isn't it?
Yes, sir.
Just quickly I will show you. But there is a difference. You can easily identify the difference between. This is electric motor, isn't it?
Yes, sir.
What is the difference? Now you can see. What is the difference? This one and this one. What is the difference? Here also the same coil, isn't it?
Yes, sir.
Rectangular or coil. This is
Yes,
connected to what here? This is connected to, two ends of the coil is connected to, what is this called?
Battery, magnet,
This one,
battery.
this one.
No, it's a magnet, sir.
What is this one?
Now this is battery.
Okay. So in the case of motor, this is connected to battery, right?
Yes, sir.
Means we are supplying some current through the coil, right?
Yes.
Okay. What is this one? This is called resistance. In electric circuits, we discussed about it.
Yes.
This is the resistance. Just we connect some resistance between the ends of the coil, right?
Yes, sir.
So we are not supplying any current, right?
Yes, sir.
Okay. But if I rotate it, what happens? That's what we are looking it out, right? If I rotate this coil, right? Hello?
Yes, sir.
If I rotate this coil, what happens? Now I am coming back to this one. Here, what I was doing, or what exactly you are looking here or observing here? Rotation of the magnet, right?
Yes, sir.
But here, I'm not rotating the magnet. Now you can see. Is there any magnet here? These lines are shown. Means these are constant, right?
Yes, sir.
So I am not rotating the magnet now. But what I am trying to do? I am trying to rotate the coil, right?
Yes, sir.
Okay. If I rotate the coil, what? Yes. Now you observe what is there through the resistance. What is that blue arrow here? Right?
Yes, sir.
Okay. What is this blue arrow is indicating? This is the current through the resistor. Now you can see the voltage, right?
Yes, sir.
So voltage is produced either way. In this way, just take the coil and put any magnet near the coil and you rotate the magnet, right? This is one way of getting the current, right?
Yes, sir.
Now I am doing another way. What I am doing? Because rotation of the magnet requires lots of energy or not, right?
Yes, sir.
Because magnet, bigger the magnet, higher the difficulty of rotating it. Suppose I have 1 ton magnet. Can I rotate easily?
Okay.
Hello?
No, sir.
No. Whereas I have a coil. Coil may not be weighing 1 ton. It may be of 10 kg or 20 kg. Which one is easier to rotate?
The smaller one.
Smaller one or less weight. So coil is easier to rotate. Either way, current is produced, right?
Yes, sir.
Okay, you can see both this one and this one.
Yes.
Here also I am getting the same electric current through the coil, but here also I am getting the current through the coil, right? Through this resistor actually. Here also there is a resistor, right?
Yes, sir.
You can see this one. Two ends of the coil is connected to, two ends of the coils are connected to two ends of resistor. So this resistor is connected to voltmeter in parallel. This is called, okay, you can see the current or voltage. Here also the same thing. But here I have a huge magnetic field or a huge magnet. Inside of that magnet, I am putting some coil in the shape of a rectangle. Two ends of that rectangular coil is connected to a resistor. If I rotate that coil inside of this magnetic field, I am getting the voltage or current, right?
Yes.
Yeah, you can see bigger. Now you can see the graph, whether there is a voltage or not. But voltage is not constant value, right? This
Yes,
is
sir.
increasing to positive maximum and then it is going to negative maximum. Positive maximum, negative maximum. Positive maximum, negative maximum. This is called alternating current. What is this called? Alternating voltage or alternating current. Why is this called alternating? Now you can see blue is the current, green is the voltage value, right? Now you can
Yes,
see the difference between the two. And you can see the zooming if I want, right? The
Yes,
value
sir.
is given here. You can see the numerical value, how much current is produced. This is almost, what is the maximum value of the current? I can stop it and then I can see. Yeah, this one, 408 volts. minus 408 volts. What are the effects? By increasing this one, you can see whether there is effect of this one or not. This is called
It's
orientation
there,
of the.
sir.
There is an effect, right?
Yes.
So I increase the magnetic field. Is there any effect of this one or not? Sure, right? As the
Yes,
magnetic
sir.
field is increasing, voltage is also increasing. If I increase the speed of that rotation, what is happening? Voltage is also increasing. This is speed of rotation, means I am spinning that coil at higher speed, right?
Yes,
Now
sir.
you can see. So if is there any voltage now? Because the coil is not rotating. Is there any voltage? No.
Yes.
Now I am getting a bit, but you can see now. If I increase the frequency of rotation, now you
It's
can see.
increasing, sir.
Yeah, it is increasing, right?
Yes, sir.
Still higher the frequency or higher the rotational speed, then still increase in voltage, right? Now,
Yes.
what is the effect of the area? Area of cross section or size of that coil? Still increase in the voltage. Now you can see, right?
Yes, sir.
So this way you can study and gather the information and then understand what exactly this one is called. Electric
Generator.
generator. Yes. How to produce electricity with the help of magnet and coil.
Yes.
So there are two possibilities. One is either moving the coil or either moving the magnet. So when we compare these two situations, which one is easier to practice or observe? Simply rotating the coil inside of a magnet, right?
Yes, sir.
I showed you both of them. This is the case of rotating the magnet near a coil. This also produces current, but this will be the difficult one. If magnet is very smaller, the current that we get will be very small. I require larger magnet, right? Definitely to
Yes,
get a
sir.
larger the current I want to get, higher the magnetic field means larger the magnet. Larger the magnet means its weight will be very large. Sometimes they use a 1-ton magnet or 2-ton magnet. You might have observed. You observed any MRI? You have the chance
Yes.
of
No,
MRI.
sir. Actually, no, sir.
You did observe CT scan or MRI scan.
No.
The machine produces 1 Tesla magnetic field. It's a huge, the bigger magnet that will be weighing around 500 kg. That magnet.
Yes.
Yeah, sometimes it's a bigger radius. Through that magnetic field, man will be passed, and that magnetic field interacts with the brain's magnetic field, and then they will see the activity, right?
Yes.
So if I want to get more magnetic field or higher magnetic field, I require larger magnets. They will be weighing around 1 ton, sometimes 2-ton magnets, 3 tons of weight, right? That will be
Yes.
very difficult. I can rotate, but they will be rotated with very slow speed. Speed is also very important for me. So what exactly the principle of generator is? Put a huge magnet, and inside of that magnet, you rotate the coil, right?
Yes, sir.
Very simple. This is the principle of producing the electric current. This is the principle we make use of. This is called a dynamo. In olden days, we used to have dynamos for cycle also.
Oh.
You have any chance of observing it?
No, sir.
You can Google it. Cycle
Yes.
dynamo. Dynamo, you can see. In olden days, they used.
Okay.
This is,
Yes,
right?
sir. Yes.
There is a magnet inside of this. Yes, this one. We played with these dynamos. We used to have. cycle fitted with a dynamo. This is the bulb, right? Or
Yes.
sometimes that bulb will be like this one, headlamp. In
Oh,
front
this
of,
one, sir.
yeah, bar, handlebar. We used to fit this bulb, and then this is the dynamo. This is fitted to that tire. It touches the tire so that this gets rotated. This is connected to one pin or the shaft. At one other end of the shaft, there is a coil. This is the magnet, right? Round
Yes,
magnet.
sir.
Instead of the round magnet, that coil rotates. So producing electric current, but you have to stress a bit so that it will get heavy, right?
Yes, sir.
It has static friction, right? That friction you have to overcome means you have to apply more pedal, or you have to apply more pressure on that. So there is a bit pressure on the tire also. The tire gets wear and tear very easily. Okay, so that's the study. Okay, that's simple mechanism in olden days they used to have, but now we are enjoying the electric or LED bulbs, right? Battery and bulb.
Yes, sir.
But these are the ones. Yet here you can go through them, and you can. And now, if you want, you can get some of them, right?
Yes, sir.
Now, this is a bit modern, right? You can go through the history. Yeah, this one. This is the bulb. Yeah, this is inside of this, right?
Yes, sir.
Inside there is a coil. This is the magnet, right?
Yes, sir.
Same. If you cut open that fan, you can see the same thing. This is a magnetic disc is there. Around inside of that one, a coil will be rotating, right? The same
Yes, sir.
principle. But it is a motor. Current is passed, and that coil gets rotated the reverse way. If you rotate the coil, current is produced. If you pass some current through that coil, you can rotate it, right? Either way.
Yes, sir.
So one is the generator is converting mechanical energy into electrical energy. Motor is converting electrical energy into mechanical energy. They are simply like inverse of the other one, right?
Yes, sir.
So principle is same. Magnet, you take a fixed magnet or a permanent magnet. Inside of that, you put some coil. If you supply some current to that coil, and if that coil is connected to one shaft, that shaft gets rotated, right?
Yes, sir.
Okay, the connected shaft, if you rotate that coil, you will get some current so that you can lit any bulb, right?
Yes, sir.
Both are almost the same. They are using the principle of electromagnetic induction. Both are using the same principle. Principle is not different, right? Either the motor or the generator. Principle is the same. You got the point? Hello? Hello? Hello?